This wave never stops. It never decays to zero. It keeps crossing the axis forever. Its total area is pi over 2. Exactly pi over 2. Not approximately, the same pi over 2 you'd get from a quarter of a circle. Except look at it, there's no circle here, no triangle, no angle anywhere in the problem, just a wave and a division by x. Before anything else, take your intuition seriously, because it's about to be half right in a way that matters. Sine oscillates between -1 and 1, and it never stops. Dividing by x squeezes it toward the axis, but slowly. At x equals 1,000, the wave is still 1,000th of a unit tall. At a million, a millionth. It's shrinking, but it is still there forever, and the axis it's spread over is infinitely long. Infinite length. Height that decays too slowly to care. That should be infinite area. Hold on to that. You're going to be right, and the integral is still going to be pi over 2. Last video, I told you your calculator doesn't run the Taylor series for sine. It reduces the argument first, then runs a fitted polynomial on a tiny interval, because the series is a terrible way to compute. Fine, let's take the series seriously exactly once, because here it looks perfect. This converges for every real number. Infinite radius of convergence. No reduction needed, no domain restriction, no fine print. And when you divide it by x, the problem at 0 disappears. People worry about dividing by x at x equals 0. Look at the series. There is nothing to divide. Plug in 0, you get 1. The function was never broken there. It just looked broken. So integrate it. Term by term, from 0 to r, every term is a power of x. This is the easiest integration in mathematics. And this is correct. For any finite r, that series converges, and it converges to the right answer. Nothing here is a cheat. Now push r to infinity. Every single term goes to infinity. The series converges for each finite r, but the terms don't have limits, so you cannot take the limit inside. There is no rearrangement, no grouping, no clever pairing that rescues this. The tool that works everywhere fails exactly here. And it fails before infinity, too. Watch what it takes to compute a modest case. To get an answer of 1.5, individual terms climb past 2 million and then annihilate each other. 6 digits of magnitude appear out of nowhere and cancel to nothing. So if you do this in single precision, 7 significant digits, you have 1 digit of answer left and 6 digits of garbage. The series doesn't just fail at infinity, it's already poisoned at 20. The series isn't wrong. It's just blind to the only thing that matters. Every term is a polynomial, and polynomials march off to infinity. The answer lives entirely in the cancellation between the humps, and a polynomial cannot see a hump. So let's go and look at the humps. Cut the wave at every multiple of pi. Between consecutive multiples, the curve is one clean arch. Up, down, and every arch has an area we can measure. They alternate in sign, and they shrink. That's the setup for one of the first things you ever learned about series. Alternate the signs, shrink the terms toward 0, and the sum converges. So add them up in order. Overshoot, undershoot, overshoot, closing in on 1.5708 from both sides. That's pi over 2, and the convergence is real. Now do it again. Same arches, but this time don't let anything cancel. Each arch is roughly 2 over k pi. Add those up, and you have the harmonic series wearing a hat. It diverges. It has always diverged, so your intuition from the opening was correct. The area under this wave, the actual, physical, paint it with a brush area, is infinite. There is no finite amount of paint. The integral is pi over 2. Those are not the same sentence. This is called conditional convergence, and it isn't a technicality. It is the whole personality of this problem. Here's how slowly the infinity arrives. A million oscillations to crawl past 10. A Google to reach 148. It's infinite the way a logarithm is infinite. It gets there, but it will never be in a hurry. And one more consequence, because it's the honest one. Conditionally convergent means the order is load-bearing. Take those same arches and shuffle them. 2 positives, then a negative, then 2 positives, and you can land on any number you like. 7, -12, pi to the pi. So pi over 2 isn't the area. It's the answer to one specific question. Sweep from left to right in order and never stop. Ask it any other way, and you get a different number. Now, how do you compute it? Start where you'd start. Find the antiderivative, plug in the limits, done. Integration by parts. Now there's an x squared in the denominator, That's worse. Try it the other way, and you've grown a logarithm. Also worse. And substitution has nothing to grab. Nothing inside is the derivative of anything else. And this isn't a skill problem. In 1835, Liouville proved a theorem about which functions have elementary antiderivatives at all, and sine x over x is on the wrong side of it. Nobody has found one yet. There isn't one. You could search for 1,000 years. So mathematics did what it does when it loses. It named the thing and moved on. That's the sine integral, Si of x, and its definition is a confession. It is defined to be the answer because there is nothing else to define it as, which leaves us with a strange task. We have to find the value of a limit we can't reach, of a function we can't write down. The way through is to stop solving this problem. Here's the move, and it's the most useful idea in this entire video. Don't solve this integral. Solve an infinite family of integrals that happens to contain it, because a family has something a single integral doesn't. A family can be differentiated. That's a damping factor. When S is big, it strangles the wave almost immediately. The area is obviously small and obviously computable because now everything converges absolutely. There's no delicate cancellation left. Nothing to argue about. And when S is 0, the envelope is just the number 1 and it's gone. We're back to the original problem, untouched. So we have a bridge. One end is a problem we can't do. The other end is a problem that's easy. And now, the actual trick. Differentiate with respect to S, not with respect to x, with respect to the parameter we invented. There it is. The x in the denominator was the entire difficulty of this problem. It's why there's no antiderivative. It's why the series was useless. And differentiating in S produces an x upstairs that eats it. The hard part of the problem was deleted by a derivative. What's left is a first-year integral. You could do it twice by parts. But do it this way instead, because it is about to matter. Write sine as the imaginary part of e to the ix, and the whole thing is a single decaying exponential. One line. Take the imaginary part at the end, so we know the derivative of the thing we want. Integrate back, and use the easy anchor to pin down the constant. As s goes to infinity, f goes to 0, and arctangent goes to pi over 2. Every value of s the formula, and the area in lockstep. So walk it home. Slide s to 0. The damping is gone. The wave is the one we started with, and the answer is pi over 2. But we're not done. Because I told you at the start that there's no circle in this problem, and I want to show you that I lied. Rewind to the single line where pi appeared. It wasn't the wave. It wasn't the damping. Pi entered through an arctangent, and an arctangent isn't a number. It's an angle. So the real question is, where did the angle come from? It came from 1 over 1 plus s squared. And that came from the fact that sine is the imaginary part of e to the ix. Sine is a circle. It always was. Turn it and you can see it. A circle, viewed edge-on from the side so that all you see is the up and the down. There was never a moment in this problem when the circle wasn't there. It was hiding inside the wave. And it gets better than that because you can see the answer as an angle. Watch. For every value of the damping, the area under that wave is exactly the angle you are looking at. Not proportional to it, equal to it. Take the damping away, send s to 0, and the vector stands straight up. It points at I. A right angle. The area under a wave that never stops is a right angle. That is what pi over 2 was doing here the whole time. 2 steps in that proof deserve to be looked at, and I'd rather tell you than have you find them. First, moving the derivative inside the integral. That is not free. It's a swap of 2 limits, and swapping limits is where mathematics goes to die. Here it's fine, and here's why. For any s bounded away from 0, everything in sight is dominated by e to the minus delta x, which has finite area. Domination is the license. The step is legal on the open interval. Second, and this is the one almost everybody skips, the last move, letting s go to 0. Notice that the first argument specifically excluded 0. It had to. At s equals 0, the damping is gone, and that is precisely where the integral stops converging absolutely. Where the infinite area we found earlier comes back. There is nothing left to dominate with. The tool breaks exactly at the destination, so we need one more fact. That f is continuous at 0. That sliding down to the boundary lands on the value at the boundary, instead of jumping. It does by Dirichlet's test. The partial integrals of sine x over x are bounded, no matter how far out you go. That's the alternating arch structure from earlier, doing real work. And e to the minus sx is monotone in x, and never bigger than 1, uniformly in s together. Those give uniform convergence on the closed interval, including 0. And a uniform limit of continuous things is continuous. That is the load-bearing wall. Everything else in the proof is arithmetic. Two quick things, because the structure we just found has consequences. First, the same answer in 4 lines, using nothing but a swap. Start from a fact about 1 over x. It is the area under its own exponential family. Swap the order of integration, and the inside is the integral we already did. What's left is arctangent again, from 0 to infinity. Pi over 2. Same arctangent. Same circle, different costume, and it needs the same care about the swap so it's shorter, not easier. But look at what it says. The trick wasn't a trick. Damping the wave and writing 1 over x as a stack of exponentials are the same idea, and both of them are just the circle in the plane again. Second, change the frequency. Squeeze the wave, stretch it, make the oscillations 100 times faster. The area doesn't move at all, because scaling x rescales the dx and the 1 over x by the same factor, and they cancel. The frequency was never in the answer, which means this integral, as a function of a, is pi over 2 for every positive a, 0 at a equals 0, and minus pi over 2 for every negative a. It's a step. This integral doesn't measure area. It measures sign. And that is exactly the job it does inside Fourier analysis, which is where you have already met it, whether you knew it or not. One last thing, go back to the very first arch. Its area is 1.8519, and it is the biggest overshoot the running total ever makes. Divide it by the final answer, and you get 1.179, 17.9% past the target, which works out to about a 9% overshoot of a full jump. That number has a name. It's the Gibbs constant. That is the ringing at every sharp edge in signal processing. It never goes away, no matter how many terms you take. It just gets narrower. And the exact height of that ringing is the first hump of the curve we have been staring at for 13 minutes. Nothing else. Just this arch, divided by pi over 2. And then there's this. Multiply this wave by a squeezed copy of itself, still pi over 2. Squeeze another one, multiply again, still pi over 2. Odd denominators. 3, 5, 7, 9, 11, 13. 7 times in a row, the answer is exactly pi over 2. Add the 15ths. Not pi over 2. Off by 2 parts in 100 billion. Small enough that a computer algebra system reported it as pi over 2 for years. 7 times, the pattern held. The 8th time, it lied to the 11th decimal place. There is a reason. It is completely deterministic, and it has nothing to do with rounding.